Hello everyone, welcome on to the GATE solution series. So in this video we are going to discuss some questions from complex analysis from GATE 2021 paper mathematics. तो चलिए शुरू करते हैं. So the question number 2 is present on your screen. इस क्वेश्चन में हमें चेक करना है कि G1 और G2 ये फंक्शन एनालिटिक है या नहीं है ऑन ओवर C. ओके, और गिवन इंफॉर्मेशन इज जस्ट f of z which is equal to u plus iv. I write in short way, u for u of xy, v for v of xy is analytic in C. इसका यूज करके हमें चेक करना है G1 और G2 analytic है या नहीं है. So what is the sufficient condition? First thing is necessary condition. We will eliminate one function by necessary condition. Necessary condition says कि if the function f of z equal to u plus iv is analytic in domain D, which implies the component function u and v satisfy the CR equations, right? CR equations are simply ux equals vy and uy equals minus vx. Okay, and what a sufficient condition is? Sufficient condition में बस एक extra चीज ये है कि CR equation must be satisfied. CR equations, right? And the first order derivative, partial derivatives, ux, uy, vx, vy must exist and are continuous in a neighborhood of point z naught, मतलब जिस पॉइंट पे हमें डिफरेंशिएबिलिटी चेक करनी है. ठीक है, if this happens then the function f is said to be differentiable at z naught. F is said to be differentiable at point z naught. Okay, so let's check what is G1. So let's check for G1 at z. It's given as, I write it as u plus I times capital V, where what is capital U is ux and capital V is minus of uy. So let's check whether this satisfies CR equations or not. What is ux now? Ux will be uxx and vy will be minus uyy. But we know because f is analytic, its component function are harmonic. But what harmonic function? What does it mean? It means uxx plus uyy equals 0 and second order partial derivatives of harmonic function are continuous. So sufficient conditions are satisfied. This condition is satisfied that partial derivatives ux, uy, vx, vy exist, are and continuous. These are satisfied. Okay, and because uxx plus uyy is 0, what does it mean? It means uxx equals to minus uyy, which implies capital Ux equals to vy. Correct? This is satisfied. Let's check for the second condition. Second condition is uy equals minus vx, right? Okay, so let's check what is uy. Uy is uxy and vx is equal to minus uyx. And we know for a harmonic function uxy equals to uyx, which implies uy equals to minus of vx. So we are through. For G1, the sufficient condition and necessary condition are both satisfied. So G1 is analytic in C. Fine. Let's check about G2. What is G2? G2 is Vx plus I Vy. Okay. G2 is Vx plus I Vy. Okay. So here capital U will be Vx and capital V equals to Vy. Okay, what is Ux? It is equal to Vxx and Vy is equal to Vyy. But we know V is also harmonic, so Vxx plus Vyy is 0, which implies Ux is equal to minus of, this goes there, then minus of Vy. Okay, but this is not a CR equation. CR equation says Ux equals to Vy. Correct? So the CR equations are not satisfied and hence simply necessary conditions are violated. So G2 is not analytic. So correct option here is G1 is analytic and G2 is not analytic. Option number B. So let's move on to the next question. Okay, so this is question number 11. This is on your screen. Okay, so the question number 11 is on your screen. What is given is we have given a region R, and agar gamma be the positively oriented boundary of the region, then we have to evaluate this integral. Okay, so what the Cauchy residue theorem says that over an integral over a positively oriented contour, integral of the function fz dz is I know equals to 2 pi I times summation of residues of fz at z equals to zk. Suppose it has some finitely many residues from 1 to n. Cool. And here my f of z is e power z upon z minus 2. So we will use a theorem or a proposition which says if a function f of z can be written as this type, some g of z upon h of z, where both g and h are analytic at point z0 such that g at z0 is non-zero, then f has simple pole at z0 if and only if z0 is root of h z of order 1. Okay, and here the function what is in the denominator, h of z equals e power z minus 2, and we know what is h dash at z. H dash at z is e power z, which is non-zero for any z. Plus any root will be a simple root. So f has pole at the roots of e power z minus 2. So let's find where the roots is. So e power z minus 2 equals to 0, which implies e power z equals 2, which implies z equals log 2 plus I times 2n pi, where n belongs to integers. So how many roots are there in our region? That जो root हमारे region में वही हमको चाहिए because of the Cauchy residue theorem. Okay, so let's check what can be n, because इस region में चाहिए अपने को roots जो भी होते हैं, roots lie on this line, straight line x equals ln2. So if I manually plug in the values of n, what I got is the roots are ln2, which is here, then this, which is ln2 plus 2 pi iota, then ln2 plus 4 pi iota. I will go straight away to ln2 plus 10 pi iota. Correct? So how many are there here? 1, and from 2, 4, 6, 8, 10. These 5 values log 2, and also I can go down, which gives me ln2 minus 2 pi iota, ln2 minus 4 pi iota, similarly ln2 up to minus 10 pi iota. So there are total 11 zeros of the denominator, so there are 11 simple poles. Okay, and also the theorem also says that the residue, continuation of this theorem says residue of fz then at the point z equals to z0, but z0 is the root of the denominator, is simply g at z0 upon h dash at z0. So in our case, what is g at z0 will be e power z0, and what is derivative denominator is simply e power z. So again it is e power z0, which is simply 0. So sorry, which is simply 1. So what is the integral now? By Cauchy residue theorem, integral of fz dz, which is equal to 2 pi I times residues, right? What is the residue at each point? For singularity to 1. So 1 plus 1 up to 1. How many times? This is 11 times. And what is asked to us? We have asked 2 pi I times integral over gamma e power z upon e power z minus 2 dz, which is simply 1 upon 2 pi iota into 2 pi iota into 11. So the answer is 11. Okay. So let's move on to the next question now. Okay. The number of zeros counting multiplicity of this polynomial we have to find in the annular region modulet from 1 to 7. Okay, good. Yeah. Now this is the circle mod z equals 1. This is the circle mod z equals 7. So we have to find number of zeros in this region. Okay. So we will use the Rouche's theorem. Rouche's theorem states that if suppose fz and gz are analytic on and inside a simple closed contour C, with the condition that modulus of fz is strictly greater than modulus of gz for all point z on C, okay, then fz and fz plus gz will have same number of roots. Same number of roots inside C. Okay. So what I will do is I will use this theorem 2 times. One when my C is mod z equals 7, another when my C is mod z equals 1. So let's for first time what my original P, which is simply fz plus gz, is 3 z power 5 plus 2 z squared plus 7 z plus 1. Okay, this is my fz plus gz. हमें बस ऐसा f और ऐसा g चूज करना है जिससे हम रोशे थ्योरम का यूज करके कुछ रिजल्ट निकाल पाए. Okay, so for first thing, step 1, I will, my c is what here? My c is mod z equals to 7, correct? So क्या ले सकते हैं हम आप? Let's take f to be 3 times z power 5 and g of z to be remaining thing, which is 2iz square plus 7iz plus 1. Okay, what is the value of fz on C? Modulus of z, which is simply 3 times 7 raised to 5, correct? This is something. And what is value of gz? Modulus of gz. I know, like by using triangle inequality, it is less equal modulus of 2iz square plus modulus of 7iz plus 1. But what is this? This is 2 times 7 square plus 7 times 7 plus 1, right? Which is 3 times 7 square plus 1, which is definitely strictly less than 3 times 7 raised to 5, right? So I am done. I can now use the Rouche's theorem because I have an f such that modulus of fz is strictly greater than modulus of gz, right? So now by Rouche's theorem, the number of zeros of fz and fz plus gz in C are equal. How many roots does fz have? So f of z has 5 roots, right? Which are all zeros counting multiplicity. Has 5 roots inside modulus of z equals to 7. Okay. So one thing what I got is fz plus gz has 5 roots inside mod z equals 7. Okay. So if I calculate how many roots are there inside mod z less than 7, I am through. Okay. Now second thing I have to calculate how many roots are there inside mod z equals to 1. Equals to 1. For this purpose, I will take fz to be 7iz and gz to be the remaining thing, which is 3 times z raised to 5 plus 2iz square plus 1. And what is modulus of gz on C, which is less equal 3 plus 2 plus 1, simply, which is 5, which is strictly less than 7, which is modulus of fz on C, correct? So I am through. I can use the Rouche's theorem now. And how many roots are there of this function inside mod z equals 1, which is simply z equals 0 is the only root, correct? Which is 1. So fz plus gz, which is my whole p of z, has 1 root inside mod z strictly less than 1 and has 5 roots inside mod z strictly less than 7. So outside mod z strictly less than 1 we have 5 roots, right? But one thing is missing here. I mean, we can straight away conclude that 4 will be our answer, because there can be a possibility that, okay, I'll draw it again. If we want to find the roots in this region, right? So we can straight away say that if 7 roots are inside this and 1 root is inside this, so all the roots are in this region. The rest of the roots can lie on mod z equals to 1. Correct? So we have to check for that possibility also. But my claim is there won't be any root in on mod z equals to 7. But because if suppose there exists a z0 such that modulus of z0 is 1 and f at z0 plus g at z0 equals to 0, what does it imply? It implies f at z0 equals to minus of g at z0, right? Which implies modulus of f at z0 equal to modulus of g at z0. But on mod z equals 1, this is never possible because we know what is the maximum modulus of g at z0, which was 5, I guess. Yeah, maximum value of mod z is 5 on mod z equals 1, and modulus of fz is straight away 7. So they cannot be equal at any possible value of z0. So this is not possible. Hence, every root now which is outside this mod z strictly less than 1 is in the annular region. So we are through. The answer to this question is 4. 5 minus 1. 4. Okay. So let's move on to the next question. Okay. So in this question, we have to find the value of 6 times a2, which is the coefficient of z square, I guess. Okay. a2 is the coefficient of z square. The function is given f of z equals to 3 times z square divided by 1 minus cos of z. Okay. This is Taylor series, right? We have to expand this function in the Taylor series. So let's try to expand. What is Taylor series of cos of z, which is 1 minus z square by 2 factorial plus z raised to 4 upon 4 factorial minus go on, right? So just put it in here. What we got is f of z is equal to 3z square minus 1 minus this thing, 1 minus z square by 2 factorial plus z raised to 4 upon 4 factorial and so on, which is equal to 3 times z square divided by z square by 2 factorial minus z raised to 4 by 4 factorial go on, which is equal to z square. I will cancel from numerator and denominator. What I got here is 1 upon 2 factorial minus z square by 4 factorial and so on, which is equal. So after this, this is simply 3 upon, I take 1 by 2 as common, so we are left with 1 minus z square by 4p 3 okay, not this. This is simply nothing but this is 4 times 3, right? I take 2 as common now. Plus minus z raised to 4 upon, there was 6 factorial, so 6 times 5 times 4 times 3 is left, which I can simply write as 6p4, right? 6p4 and go on, okay, which is equal to 6 times now 1 plus the whole term here, this term plus same term squared and go on. So in this thing, I need to find the coefficient of z square, right? Because I need to find a2. So when you observe, this thing has a term of z square, but if you go further, the minimum term squared, minimum term is of z square, whose square will be degree of 4. So there won't be any z square term further. So the only coefficient of z square is 6 times 1 upon 4 times 3, right? Which is equal to 1 by 2. So this is a2. What we want is 6 times a2, which is equal to 6 times 1 by 2, which is 3. So we are through. The answer to this question is 3. So this is all, guys. These are the questions from complex analysis in GATE 2021 paper. Hope you liked the video. Thank you.